right now. All right, so there was some questions on something or other. Number 2. Here. This one? I don't think I could do that. It looks hard. Which one? Both of them? All right, let me sketch the schematics first before I switch over. What if I do it and it makes it look easy and you get angry? You're already angry? All right, let's do this one first. And this is the 1 micron process, so we'll see how it goes. We are recording, right? Is anybody actually still using the videos?
Yes.
All right, so what does this problem ask? Anyways, just asked to find the drain current. All right, so let's find the voltages first. What's the DC voltage here? What's the DC voltage there? What's the oops, let's change colors. What's the AC voltage here? 0. I can't change that 5 volts. It's AC ground. What's the AC voltage here? What does minus 1 millivolt mean to you? Nothing? Which means out of phase, yeah. So if this was cosine, if this was 1 millivolt cosine, whatever, this would be 1 millivolt cosine, whatever, plus 180 or minus 1 millivolt, right? Does everybody see that? Like, this is like really clear to me. So if it's not clear to you, I want to know. Cody, is it clear? All right, clear as mud. So now let's go. Is that an unreasonably long homework assignment? No? You want them longer in the future? All right. So let's calculate the DC. And that's equal to, I'm going to use the book, 1 micron process. The KP isn't a function of the sizes. This is for, oh, this is even a 10 by 2? Huh. Okay, 10 by 2, we use 120 microamps per volt squared and 0.8 volts. Is anybody enjoying the weather? No. You don't like the cold? Cold sucks. All right. Have you ever seen a bumper sticker that says summer sucks? They like people that like to ski. They always do that. Summer sucks. We want the snow. I'm like, screw that. Until you start having to get up and shovel it. That ain't fun. All right, so what is this equal to? 120 divided by 4 is 30. 30 times 10 is 300 times 0.35 squared. That's 0.1225. Does this all look familiar? And then I go say, all right, that's times 300. That's equal to 36.5 microamps. Anybody get that? And you simmed it and it didn't work? Really? This is fine? No, that's fine. Let's do it anyway. Is anybody using these simulations?
My sim is from the AC analysis and the transient.
What? Does he have a bug in his program? File, save as. This will be lecture 4, example 1. So just a little secret. If you go over to the, does anybody know this song? Walking in LA? Missing persons. Only a nobody walks in LA. I always think of that whenever I walk around LA. Only a nobody walks there. That's what I am. All right, anyway. So I go over here to LT Spice. And I go over, was anybody thinking about the food truck when they saw that in the background? Wonder what kind of good food they had. And of course I didn't have the time. So here's some older versions of LT Spice. This is LT Spice 4 and LT Spice 12. He started doing some crazy stuff, and so back a while ago, I just kept LT Spice 4 because I'm like, this keeps me immune. So if he changes things, I have an older version. So just so you know, if you want to download and run LT Spice 4 or try something, you can. Remind me, how did I get there? Just delete the HTM to get the directory listing, and there you go. All right, you can find out all of the secrets. Ooh, what are the secrets? Ooh, we can't do it there. What are his secrets here? Oh, yeah, there we go. All right, let's rename this model to N_1U. And then the width was 10. And that's what it was in the homework too, right? Okay, and then this was 5 volts. What? I'll change that. Give me a sec, man. And then this was 1.15. And then let's hit roll them. All right. Save. Whoops. Run. Yeah. I know that already. All right. I had a flashback to when my son was young and he was learning to talk, and I'd tell him something. I know that already. All right. And then the ID is 33 microamps, and we calculated 36. Pretty close. Looking good. You know how to look at the small signal parameters. All right, let's do file, save as, example 2. And then hit .ac. Actually, how do you want to do it? You want to do .ac or transient? Gabriel, what do you want? Let's do AC. He didn't hesitate. You know why he said AC? Because that's what he did in the homework. Let's do 1 through 10K. All right, and hit run. And then let's go, before we do that, go view, spice error law. Wait, where is it that we see the small signal parameters? I'll come back to that. It's probably under... I know I just did it. Okay. Sound essentially short channel device. This is a dot, oh, OP, yes, there we go. Let's do that. Actually, I'll come back to that. So we're gonna go save. And then I'm gonna look at the current on here. The DC, it still says 33. Who was tweaking me? 33 microamps, all right. And then let's look at the current. AC current that flows. Boom. Let's go linear. I don't like dB. It says 133 nano. And then I want to find out what the input resistance is. So what do I do? 1 milli, that current into, what's the AC voltage on the drain? 1 millivolt. Anybody agree with that? Then hit enter. And I get 750K. Did anybody get that? Did you guys get that? Sony? Well, I don't understand. I just did the AC current divided by the AC voltage. Yeah, problem 2 for R out. Okay, so we're going to remember that? Yes.
You also do that with transient because they give like 2 different results.
Yes, let's do that with the transient, but let's see what the dot OP gives us first. Any questions on this one? I'm going to go ahead and swing over because I can't remember jack squat on this stuff because it's like ready to be flushed as soon as I walk out the door. I'm going to put R out equals 750K sim AC. We all good? All right. So then I'm going to go close this, and then I'm going to go right click, view, list, and I'm going to go here, and I'm going to do file, save as, and let's go save as example 3. And let's change this to .op, and that will, come on, Shelly, .op. And hit save, hit run, and then I'm going to go over here and I'm going to go to view spice error log. So this gives you the small signal parameters, and you see this GDS. What does that mean? The conductance between the drain and the source, but I want resistance because if you look, I put resistance here. So how do I go to get from the conductance GDS to resistance? Let's see what we get. Calculator. Does everybody know when you hit start, if you just start typing what you want, like notepad, calculator, it pops up? All right, just checking. 1 divided by 1.33 EEE 6 change sign equals, woohoo, 750. So far, so good. Now let's go do the third or next simulation, which is here. Do file, save as, and then we'll do example 4. Question? Yes, no? All right. Here, then I'm going to go change this to sine, and then my DC offset will be 5. My amplitude is 1 millivolt. Frequency, let's just use 1 kilohertz. And no delay. Looking good. And then I'm going to right click here, transient, stop time. How about 5 time constants, or 5 periods, so 5 milliseconds. Actually, let's not even look at the first 3 milliseconds. Hit OK, hit run, and then I'm going to plot the current after I subtract out the DC. Minus 33.33911 U. Does everybody understand when it's transient, I have both DC and the AC? Any questions? Does it seem like I'm doing magic? Should I have done this last time? I did do it last time. Oh yeah. Damn it. The magic. There should be a default, like if it has below a certain number of components, it's just automatically, you don't need to do this. Plop that down, hit run. All right, and so I've got a current of about, peak is 273 picobabies. And so I'm going to get the calculator out, CAL, boom, and do, oh wait, before I do that, can I just take that current and divide it by into 1 millivolt? Like I did with the AC. Your response is colloquially, hell no. Why? Because right here, when it crosses 0, you try to do the division, what's going to happen? You're going to get a huge spike. Why can I do it with AC? Because AC is only looking at, say, the peak, not looking at the sinusoid. So I can't divide sinusoids out. All right, looking good? So I'll go back. I feel like I'm in my own little world now. Is anybody not following? Chris Barr, you following? Sean, are you following? All right, so I'm going to go back here. I'm going to go 0.001 divide by, I don't know, I'm just going to say 275 E 12 change sign equals. And that says 3.6 meg instead of 750K. Yeah, 275 picobabies. So I did 275 times, yeah, 275 times 10 to the minus 12. So is this the problem you were having? And so it's off by 4 or 5? Yes? No? Anybody follow? Anybody get this? I'm trying to get a feel for what's going on. That problem was hard. I'm going to finish the hand calculations, but before I do, does everybody see that there that's 3.6 meg and it's like 5 times different than what I calculated? Okay, I'm going to do this. I'm going to save it, and I'm going to show you something, and we'll talk way more about this later. I'm going to have to change the DC offset, but that's fine. I'm going to change this to 3 volts. So, I mean, it shouldn't affect, I'm still in saturation. I should get the same exact AC current. And let's remove this, see what the average is. And that is subtracting 32.73333 micro. And there I get 350 pico. What's going to happen to the resistance? It's going to go down back towards what I calculated, the 750 millivolts. So the key point here is that you can change the voltage across the device, and it's changing the resistance, which it shouldn't. Let's continue on with the problem. Before I do, any questions? Is everybody like, what the hell's he doing? Michael, are you like, what the hell am I doing? All right. So let's hit no, because I want to leave it the way it was. And then let's not calculate the value of lambda. Let's simply go back here and use the one that's in the back of the book for that other size, which is 0.01. So I'm going to calculate using hand calculations. My R out is equal to, so let me ask you this. When you have your R out, when you, or let me ask you, when you took 320, did you talk about R out for like bipolars or MOSFETs? You did? And what would you use for R out? If you did bipolars? Does the early voltage ring a bell? Did you talk about early voltage? You're the only one saying yes. I'm having doubts that anybody remembers. All right, so I'm just going to calculate. 1 over 0.01 times 36 micro. Anybody agree with that? So what is the 0.01? Lambda. So let's see what we get doing hand calculations. 36 E6 change sign times 0.01 equals shift 1x. All right, what is that? That's 2.7. So between the two extremes. All right, anybody get that? And then when you did the sims, you got this one or the 3.5 or whatever it was. So the other sim, I should write that down, was it what was the number? 3 point what? Oops. 3.69? Roll them. And then that was 27. Let me do it one more time. Oh, I don't want you. I want the calculator. I should have just dragged over while I had it open. Let's do 0.001 divide by 275 E12 change sign equals 3.6 and just say 3.6 meg. For transient. All right. Does it bother you that this changed? Well, there's a lot of parameters. It's a real device. It's not a fake device like in 320. In 320, they're going to come out exact. They change even more for the short channel process. Any questions on this one? Well, you're not going to get exact values. That's the problem. So when you try to get a simulator, like I'm in the ballpark, I hand calculated 2.7 meg and I got 3.6 meg. Now, if I want to get it closer, I just adjust the VDS because it's not supposed to be dependent on the VDS, but it is, as we saw. We can get almost exact value if I go to 3 volts. Even though the slope of the line is changing. You know what? And I'm saying that and I'm like, they don't have a damn clue what you're saying. So let me say that. So here is the IV curves, right? This is ID, this is VDS, and what is this? Constant with what? VGS equal constant. Which one is this, the plot for? My house example? Me turning the valve on and going out in the street and turning the main water on. Does everybody know that if you live in a house, there's a water main in front? Yeah, it's outside. All of them are outside by the meter. You can turn the meter off, and if you don't pay your water bill, they come over and put a lock on it. Right? Everybody here pays their water bill, don't they? There's some laws, unlike power and other things. If you have the money to pay it and you don't, then they'll do that. But if you don't have the money, then they won't. All right. Whereas the power company doesn't give a damn. Turn off your power. You can boil in the heat. They don't care. So what's the R out in this plot? That's a good question. Yeah, 1 over this slope, right? Well, if I'm operating here versus here, do you expect R out to change? No, you don't, but we just showed it does. And we're going to show it even more. I'll cut to the chase real quick. If I go, we'll do this in a couple lectures, but if I go to the end of chapter 9, and this is why I don't want you to be too uncomfortable. If I go to end of chapter 9 and I look at how R out changes with, this is why PowerPoint's good. If I look at how output resistance changes with VDS, look at here, as I start to change VDS, here's where we start to enter VDS up, and then it comes up drastically. That's a factor of like a factor of 10 change with VDS. And here it's not as much, but it's still changing a little. All right, let's zoom in on that, actually. All right, any questions on that? Any other homework questions? Did anybody look at last year's lecture? Don't you think I should hide information from you? I'm spending my life watching videos. We ready to do example 9.5? Okay, that's this one right here. If you look, that is right here. So we'll start example 9.5 today in various analysis technique, AC, DC. All right, and then we'll finish that up next time. Do you think we have a quiz today? Of course we do. Don't you feel alive? Not dead inside. He said his quizzes make me feel alive, but after I take them, I feel more like I'm dead inside. All right, example 9.5. Let me sketch that. Here's what we have, and this is a differential amplifier. So here's VDD. Here's my PMOS, which I'm going to label the source, drain, and gate. Here's the source, gate, drain. Notice C and CMOS means complementary, so that when we look at the PMOS, the source is on the top, the NMOS, the source is on the bottom. So here I've got the drain, source, gate. And then going to that gate, I have 1 millivolt. And then 2.5 volts. Coming down, and I've got 40 microamps. And then this is M3. This is M1, M2. Then coming up here, I've got a device with the gate grounded and M4. And all of the devices, NMOS are 10 by 2. PMOS are 30 by 2. And then this over here is 2.5 volts. All right, so I want to go through, and first, whenever you're in analog design, the first thing you do is you do the DC biasing. Why do we do that first? You need to know what's in saturation, what's in triode, and then once I know that, then what do? Then I do calculate the small signal parameters. So this problem is very similar to what I put on a PhD qualifying exam in electronics, because it goes through basically everything. Okay? So let's use orange to write DC. What's this voltage? I don't know. What's this DC voltage? 2.5. What's this DC voltage? So this voltage and this voltage are the same. What can I say about this VGS and this VGS? Why?
They're tied to the same source.
Yeah, they have the same voltage on the gates and their sources are tied together. Everybody sees that. Okay, so if the VGSs are the same, what can I say about, assuming they're in saturation, what can I say about the current flowing in each? They're the same, and what is that current? So far, so good. Did you cover diff amps in 320? All right, that's probably a little advanced. All right, that's what this class is for. All right, so now tell me how to calculate VGS. VGS equals the square root of 2 times 20 mic. This is, well, let me tell you where a lot of students make a mistake, is it's 2 times ID over KPW over L, correct? So that's 120 micro times 10 over 2. For these two, a lot of times the students will forget that half of the current, the tail current here, flows in each MOSFET, and they'll use 40 here instead of 20. Okay, plus 0.8. What's the 0.8? Threshold voltage. So I go, okay, so I've got 2 times 20, which is 80. 80 divide by 1200. The micros cancel. Equals, and then square root plus 0.8. And that gives me VGS equals 1.058 volts.
Divided by,
I just took the 2, flipped it up, and got 80, and divided by 1200. Now, qualifying, PhD qualifying. What does that mean this voltage is? I don't want to get it wrong. Fail my qualifier. Minus 2.5 equals, this voltage is 1.44 volts. Now it's going to be a little bit less than that because of the body effect. And what was the body effect? People that took 421? Don't try to hide there, Cody. That means the threshold voltage goes up when the source and bulk aren't, or source and body aren't at the same potential. The threshold voltage go up. So instead of having 0.8, it would be like 1. So when you calculate, and this says, oh, it's now 1.24, it's because the threshold voltage is not 0.8. This body steals charge, and I have to use a larger threshold voltage to turn it on. All right? Okay, how many people understood that? Be honest. If I asked you on a quiz, what's body effect, could everybody explain it? So let me explain it, because I don't think you can, and I don't want to be magic here, because it's not hard. Well, everything's not hard when you understand it. And then this is the P plus. And so the P plus goes to ground. Substrate's always at ground, it has to be. And then here, I've got this voltage at some voltage. This is the source that's not going to be at ground. It's going to be here like I'll just put 1.44 volts. And this is 2.5 volts. And this is whatever it is, we don't care. So I'm going to ask some simple questions, so don't turn your brain off. When I apply a positive voltage here, what do I attract underneath the gate here? I've got electrons, right? Does everybody see that? However, because the body's at ground. However, my source isn't at ground, it's at a higher potential. It's at a positive potential. Let's draw that on here. Yay? That source is sitting there, and I've got these channel electrons in there, and it says, hey, I see a positive charge. I'm going to steal some of those electrons over here. So it steals the electrons. So you know what? I got to work harder with the voltage here to invert that surface and attract the same number of electrons. So that's the same as the threshold voltage going up. The body is stealing, because the body effect, the source isn't at the same potential as the substrate. That source potential steals electrons from the channel, and I got to work harder to invert it. Does that make sense? So that's why when I do the sim and I look at this, this is a little bit lower because the threshold voltage is a little bit higher. You got to work a little harder to get those electrons attracted underneath the gate oxide. So if I say I need 1,000 electrons here, then I connect the source up to a positive voltage and it steals 200. Well, then I got to apply a larger positive potential here to attract the electrons up to the positive potential to get back to 1,000. So that means just invert the surface, my threshold voltage goes up. All right, we good to go? So I know this voltage is 1.44. I know this voltage is 2.5. I know this voltage is 2.5. I know the current in each branch is 20 microamps. Now I'm ready to calculate the stuff up here. Before I move on, are there any questions? So if I were to give you something like this on the quiz on Wednesday, no one would be challenged, right? This is 2.5, right? The VGS is 1.058, so it's just dropping down to 1.058. Okay? So now I'm going to go do the top part of the circuit. Now notice, can I use the NMOS here to calculate what this voltage is and this voltage is? No, because they behave like current source. They're each pulling 20 microamps. I got to use the pmos to calculate those voltages. Does everybody see that? No one's going to miss this test on their this problem if I put it on the PhD qualifier, right? What if I put the pmos flavor? Maybe we should work on that before we move on to the AC part, just to make sure. All right, because there's no excuse. All right, everybody good? What's the current flowing here? 20 micro. What's the current flowing here? 20 micro. Okay, so now I ask, what is this voltage here? VSG, well, 5 minus VSG, so I'm going to calculate VSG, right? So this is the tricky part, because this voltage is VDD minus VSG. So then I write VSG equals the square root of 2 times 20 micro all over 40 micro times 30 over 2 plus 0.9. What's the 40 micro? Transconductance parameter, Kp sub p. So what can I do? Boom, boom, and this becomes the square root of looking good? Let's calculate that. 1 divided by 15 equals shift square root plus 0.9 equals 1.158 volts. Here's where we get a mistake. What is this voltage right here now? 5 minus 1.158. It is 3.842. Okay, I'm going to ask you a question. You're going to tell me the answer. Why is this in saturation? Gate and drain are tied together and there's a current flowing through it. Remember we went through this at the beginning, a few lectures ago or whatever? Okay, but what's the state of this one? Oh, I don't know. Let's find out. What is VSG? Everybody see that? And for this to be in saturation, well, let me ask. Is VSG greater than the threshold voltage? What is the threshold voltage for the pmos? 0.9. So is that VSG greater than the threshold? Yes. So I know for saturation, VSD has to be greater than or equal to VSG minus V threshold P. Okay, so that is 5 minus 0.9 is 4.1. That means this volt, okay, wait, so VSD has to be greater than or equal to 4.1. So what does this voltage have to be for saturation? If VSD has to be greater than or equal to 4.1, what does this voltage have to be? Less than or equal to 0.9, right? Because 5 minus 0.9 is 4.1. This voltage has to be lower than 0.9 for this to be in saturation. So I look at it and I go, wait a sec. There's no way for that to happen because this voltage is 1.44. There's no way for this to be in saturation then. Because if this is at 1.44, how can this be at less than 0.9? It would mean current's flowing backwards. Does everybody follow that? Sony? Okay, that's at 1.44. So what's the lowest voltage this could be at? Assuming this device is on all the way. What's the lowest? I'm going down the stairs. No, what's this voltage? The lowest it could be at in this circuit with this device all the way on. Going to 5, I'm going to 3 point whatever, I'm going to 1.44, I'm going to ground. I'm going down the stairs. Going to 5, going to some voltage, going to 1.44. Assuming this is all the way on, what does this voltage, the minimum it could be? No, you're making it hard. Think clear. If I'm on the 4th floor of this building and I know that you're going to be on the 1st floor, can I say that I'm going to be on a lower floor than you without passing you? No. So if I'm here and I'm at 5 and I go down, what's the lowest this can be if this is at 1.44? No. Wait a sec. If this MOSFET's all the way on, what's this voltage and this voltage? You guys are killing me. Your thought process is so... What?
It's got to be greater than 1.44 volts.
Here. What? There's the MOSFET. I'm doing this. I'm doing this. I'm doing this. I keep doing this until I've cranked VGS up so much. This is ID. This is VDS. I keep going up and up and up and up. What ends up happening to VDS? Goes to 0. Switch turns on. So that means this is at 1.44. If the VDS is 0, what's this voltage? 1.44. These are trivial questions. You go for a job interview and they ask you that, they're going to be like, what the hell? All right, so what's the lowest voltage that you can have there? 1.44. Well, why not 0.9? Oh, wait, you're telling me you're going down in the basement some magical way, like transporter, and then coming back up and you're going to be over here? I don't get it. You see, I'm just thinking, I'm going from the 5th floor, down, 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 do, do, do. Oh, now I'm at some floor. Then I go down. Hey, now I'm on the 1.4 volt floor. I know this floor's got to be above the 1.4 volt floor. But you're telling me 0.9 is like I've got this and I magically transport down here and then, oh, now I'm going to go back the other way. And I'm like, I can't even get my head around that. Okay? So everybody got it? All right, let's go back. I don't want you to miss these questions. So this voltage from our calculations has to be at less than 0.9 when I VSG is 5 volts for this to be in saturation, but it can't ever be below 1.44 because the sources are at 1.44. So it's always going to be in triode, but I didn't calculate what the resistance is looking into the drain of a MOSFET that's in triode. I calculated it when it's in saturation, but not triode. So why don't I do that real quick? Okay, then we'll come back to this. What's the class I've taught the most in my life? I don't think, man, maybe, no. No. Let's go back. Look. Microelectronics, 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 microelectronics. Let's see, when I first came back to UNLV, what did I teach? Engineering electronics. Engineering electronics. I'm wondering if I should go back to teaching that. Screw circuits. All right. Which way do you want to do the, you want to do it for the PMOS? Yeah. All right. So here's the PMOS. What is the source and the drain, sourcing gate for small signal analysis? I'm going to see if I can skip a step. What are the source and drain? I'm applying an AC signal here. For AC analysis, what are the AC voltages? All right, screw AC analysis. What is the AC voltage right there? Zero. What's the AC voltage right there? Okay, so I'm going to write those here. Anybody got a problem with that? So what's VSG then, AC? 0. If I go plus minus, what is this voltage right here? VT. What is the source to drain voltage? Looking good? Now I drew this. Not showing DC biasing. Everybody got that? So when I go, hey, there's no VGS, no one's going to say, how can that be? You have to have at least a threshold voltage there. Well, I do have a threshold voltage. I have 5 volts, but both this and this are at AC ground. Okay, so now I'm going to ask, what is the current I test? And how's I test related to I drain? Equal and opposite. So then I go, now I've done this a zillion times, so if I'm not being clear, you need to tell me. Okay, so I go over and I say, well, if I'm in triode, that means I'm over here and I'm finding the slope there, which I'm going to call R channel. Everybody agree in R triode, I'm over here? And refresh my memory, what was the equation for triode? No 2. So this VDS is this VDS, and at the boundary between triode and saturation, VGS minus V threshold N is VDS. Oh, whoops, that's not squared. And so that becomes VDS times VDS, or VDS over squared minus VDS squared over 2, or 1/2 VDS squared, and that gives me the 2 out over 2, and that gives me the 2 out there. All right, we're going to use this. I'm assuming nobody's following. So I'm going to define R channel, or 1 over R channel, as the same old thing, the derivative of, well, that's 1 over R channel, I drain over and I'm not going to worry about the minus signs because it's minus VSD, whoops, VSD. Because it's minus VSD and minus ID. All right, and so if I take the derivative, this becomes KP times W over L times derivative of this with respect to VDS is just VGS minus V threshold N. The derivative of this with respect to VDS is just VDS. We'll write it like this. And that's times the derivative of VDS with respect to VDS, and that's just 1. So if the DC is much, much greater than the AC, this approximates to our channel is approximately 1 over KP times W over L times VGS minus V threshold N plus the VDS. And a lot of times you don't need the VDS because it's assumed, sorry, I said it right at the beginning, it's much, much less. Then this is small, and you can even and I'll just show you where it is in the book. Let's do this. Let's see, where was that? Triode region. Right here. The bottom of page 285. There's our friendly equation. There's 1 over R channel minus KP. And this term, if it's small, goes to 0. So we can write it out just to be exact, like this, which I just did. Oh, what's VDS sat? VGS minus V threshold N, what I just derived. And then this is R channel is just VDS sat, and we neglect the VDS if VDS is small. It's going to be very small here. We're going to sim it. Who understood that? All right, few people. You know what? Because I want you to understand, let me do it one more time a little clearer. The derivative and all that. You understand how I apply a test voltage? I look at the AC current that flows, which means I plug in the equations here for the test voltage. I'm going to do it nice and slow on the next page. You know why? Because I can. What song is that? Fat Boy Slim. Can. Yeah, that's probably an old song at this point. All right, so let's do that. So we'll write R channel is equal to the derivative of ID with respect to VDS, which is equal to minus the derivative of I test over minus the derivative of V test. Right? So far, so good. And that's equal to the derivative of VDS of ID, which is the derivative of VDS of KP times W over L times, I'm going to be really verbose here, VGS plus VGS minus V threshold N squared with respect to VDS minus VDS squared over 2. And what is this voltage here? 0. Right? And then I can rewrite this as, what's the derivative of this term with respect to VDS? Yep, VGS minus V threshold N. And what is VGS minus V threshold N equal to? This is why I'm doing it, because I didn't think anybody caught that. VDS sat. That's another name. When you say VDS sat, it's just a lazy way of saying VGS minus V threshold N. And then what is this term, the derivative? Okay, but what is VDS? That's equal to this plus this, which for the DS much less than VDS, this is approximately a VDS. And what was that approximation I just made? Called small signal approximation. Small signal approximation. Assuming that it's not wiggling a lot when I'm biased at the point, it's just moving back. I mean, I'm not turning the knob a lot relative to where I turned it on. All right, so there I go. And would you agree that if VDS is small, then our channel is approximately 1 over, then this term goes to 0. And this is just Kp times W over L times VGS minus V threshold N. How is that? Better? Okay, and what is this term right here? Just out of curiosity. GM. So the channel resistance is approximately 1 over GM when it's in the triode region. All right, we ready to go back to the example? So we go back to the example. We have the following. We have that, and let's just focus on this side, because I did the 8, oops, shoot. Focus on this side. What's the current flowing there? 20 micro. So the DC voltage here, let's calculate. We know that AC, and I'm going to use this next time, is 1 over Kp times W over L times VGS minus V threshold N. So you can read that example in the book. So you can come in and go, you know, your guru stuff, and I know what I'm doing. This voltage here, though, is going to be 5 or VDD minus VSD. Looking good? Okay, and so how do I calculate VSD? Oh, I use VDS, that's sorry. So used to using VDS, that's supposed to be VSD. All right, how do I calculate VSD? You say, gee, you're not challenging me. I got the currents 20 microamps. And I've got Kp is 40 microamps times 30 over 2 times VGS, which is what? Don't all scream it at once. 5. That's VSG. Anybody not follow that? Where am I pointing to? Right here. Anybody follow that? Minus 0.9 times VSD minus VSD squared over 2. Now I'm lazy, as you all know. So I know that VSD is going to be small, so let's say it's 10 millivolts. How is 10 millivolts squared compared to 10 millivolts over here? 0.01 times squared is 0.0001. So I'm going to say this is approximately 0 for all I care. Okay? And now I'm going to get that VSD is equal to, let's see if I can do this right in my head. So moving this over, sliding this bead over would give me 1/2 on this side. I can cancel the 1/2 here with this. And so then I could move this over and I get 1/30. And then this is 4.1. And that gives me 30 times 4.1 equals shift 1x, 8.1 millivolts. So what is this voltage then? $4.9919, if I did the math right. Make sense? So to calculate the DC voltage, all I did was plug in an equation. Now let's check my assumption. Did anybody follow that? And again, what am I doing right now? DC analysis straight out of the book. I have not changed example 9.5 at all. So if you're struggling, you can go read that example, look at the simulations, and go through and make sure you follow. For next time, I'm going to do the AC portion. My assumption was that this term was small. Let's see, 8.1 milli, let's square it, see what it is. That's 66 micro. So let's add 66 micro with 8.1 milli. Plus 8.1 E3, change sign equals. How much did we change? Not much. Especially after you divide by 2. Any questions on this DC calculation? When we come back on Wednesday, what are we going to do? The AC portion of this example, but make sure you got the DC. And again, this is a very common, diff amp we'll use it the rest of the semester actually. It's a very common circuit, so you want to master it. And then if you're going to take the qualifying, you want to get a PhD at some point here, you want to take the qualifying exam, then it's good to know this problem because I love this problem and I love to modify it. And if I can, next time after we do the AC, remind me and I'll do the PMOS version, all right? And we'll go through it pretty fast. All right, any last second questions before we go illegal? All right, let's stop.